This video is for Monday, August 8th, Math 1325. We're scheduled to do 6.1 and 6.4 today. We don't do every section of chapter 6. So 6.1. Today is 6.1 and 6.4, then Tuesday 6.6 and 7.1, and then 7.2 and 7.3 on Wednesday. So just 6 assignments this week, 2 per day. 6.1, we dealt with a couple of ways last week of finding local or relative maxes and mins. Now what we're looking for are absolute maxes and mins. So find the location of any absolute extrema for the function whose graph is shown to the right. At what x-coordinate, if any, does an absolute maximum occur? Okay, so two things here. If you have a function that has a interval given, like if they say it only goes from A to B, and I don't know if that's the case here because these arrows are a little misleading. If it only goes from A to B, and you have a continuous function, if the interval is closed to where it stops at A and stops at B, then you're guaranteed to have an absolute max and an absolute min inside that interval somewhere. But if it goes on forever, this is kind of implying that this is going to just keep going up forever, this is going down forever, then it doesn't have a absolute max or min. It goes to infinity. So I'm assuming with that arrow pointing up that it goes up forever, then there would be no absolute maximum occurs. You could have a graph like this, and if they said in the directions, we only care about the interval from A to B, then that could change that, but it doesn't say that here, so okay. And then there would be no absolute minimum either because it goes down forever. Okay. Looks like the same problem. 6.1, 6.3, okay. The graph didn't really change though. So I'm not sure why they're giving me this problem twice. No maximum. No minimum. Okay, so that was because it went up and down forever, that happened. But this is the situation right here. You have a closed interval because there's a closed circle here. Closed interval starting at x1. The graph is continuous. And then it stops at x4. So if you have a closed interval, you're guaranteed to get an absolute max and an absolute min. And they can only occur at endpoints or critical numbers, places where the derivative would be 0 or undefined. So that's why they've marked these 4 spots off. We got the 2 endpoints always when it's a closed interval. And then there's this spot right there would be a critical number because the derivative would be 0 there, flat tangent line, and then there as well. So these are the only 4 candidates that could be absolute maxes or absolute mins. And then all you really do is make a list if you have an equation, or in this case, look at the graph, and what is the y value of each of these spots? Well, this is the lowest y value for sure. And then this y value is a little higher than that one, but this one's higher than both of those. So x4 has the highest y value. That's the absolute maximum. x1 has the lowest y value. That's the absolute minimum. So, okay, so they want you to, for each of the 4 x's, tell what's happening there. x1 is the absolute minimum. There's no spot anywhere on that graph that's lower than that. x2 and x3, there's nothing special about those. They're not absolute extremum. There's points higher and lower than those 2 spots. But you can get max or mins at critical numbers. It's not that they have to only be at the endpoints. So this problem's a little misleading in that regard. And then the fourth one was the absolute maximum. What is the difference between a relative extremum and an absolute extremum? You must have a continuous function, okay? And they're doing just closed intervals here at first, but later we'll do open intervals too, or infinite intervals. Okay, can have more than one absolute max and absolute min, but does not always have a relative max or min. Can have more than one. Can have more than one. Can have more than one. Trying to see what the difference here is. A continuous function on a closed interval can have more than one absolute maximum. No, it's guaranteed to have only one. Now there can be a tie if two spots are tied for the highest, but it can't have more than one if they're different. Can have more than one absolute maximum, absolute minimum, but does not always have a relative max or relative min. Can have more than one relative maximum, relative minimum, but does not always have an absolute max or absolute minimum. More than one absolute max or min, but it only has one relative? No. And can have more than one relative max and min, but only one absolute max and absolute minimum. Yeah, see, that's the case, is that you could have a lot of relative max and mins. Local max and mins are just places where the graph changes directions. So you could change directions a lot and have more than one of those. And then if the two endpoints were like the problem we just did, if the two endpoints happen to be the highest and the lowest spot, then that's the only absolute max and absolute min in the whole graph. Okay, so now we're up to the point where we aren't given anything, we just have to do it ourselves. So we have a polynomial function and we have a closed interval. So on a closed interval of a continuous function, and all polynomials are continuous, you're guaranteed to have a maximum, an absolute maximum and an absolute minimum. There can be a tie, but the value can only happen once. And the only place they can occur is the endpoints of the interval or any critical numbers inside the interval. So the first thing you're going to have to do each time is find the critical numbers. We've been doing that for a couple of chapters now. That's why they're called criticals. They answer almost everything we do. So f of x is 3x to the third. Three x to the third minus 3x squared minus 3x plus 8. Now they gave us a really tight closed interval, -1 to 0. There's not a lot in between that. So there could be two critical numbers from the function itself, because the derivative is going to be a squared function. 9x squared minus 6x minus 3. This is never undefined, but it could be 0 twice. And we can divide by 3 to make things smaller. So 3x squared minus 2x minus 1 equals 0. So the only way to get 3x squared is 3x times 1x. We definitely have to have 1 times 1 in the back, and there's definitely one positive and one negative. And we need it so it subtracts to a -2. So that means the 3 needs to be negative, and the 1 positive, so that way you'll have a -3 plus 1 is a -2. So this is x equals 1. That's one of the critical numbers. And if you subtract 1 and divide by 3, if you have to do that slower, that's fine, but x equals negative 1/3 is what that would be if you solve that equal to 0. Negative 1/3 is between negative 1 and 0, but positive 1 is not. So we lose this one just because it's not in this interval right here. So we make a little table here, and only endpoints and critical numbers inside the given closed interval. So that would be negative 1, negative 1/3. Whoops, I forgot the negative there. Negative 1, negative 1/3, and 0. These are the only things we have to check. And then you just do f of x, literally. It's the y value of these. Not plugged into the derivative, but just the original function. So I need to plug in negative 1, negative 1/3, and 0. 0's easy because all the x's will disappear. So the answer is 8 when you plug 0 in. So I can do 3 times negative 1/3 to the third power minus 3 times negative 1 divided by 3 squared minus 3 times negative 1/3 and plus 8. So the y value when I plug in negative 1/3 is 8.5555, and then if I do math, enter, it turns it into a fraction because that's what they usually prefer. 77/9, but know that it's about 8.5. 77/9, approximately 8.6. And now I can hit second enter and call up the last statement, second enter twice to call up that statement, and I can just delete the divided by 3's. Be fastest way to, so I don't have to retype the whole thing. So now doing f of negative 1, I get 5. So once you have your list of all possible endpoints and critical numbers inside the interval, these are your only chance to have absolute max or mins, and you're guaranteed to get an absolute max and an absolute min. So they're unique in their value. 5 is the absolute minimum value because it's the smallest number in this possible list. And then this 8.6, which we're going to call 77/9, that's the absolute maximum. There can be a tie. Say this was 8.6 and both of these were 8s. Then you could say there's a tie for the absolute minimum, but the value, there's only one absolute value minimum value. It would be the 8 if they were both 8s. And then I could say the absolute minimum is only 8, but it could occur at both negative 1 and 0 potentially. So there can be a tie for the x values that create an absolute max or min. But in a closed interval, you're always going to get only one absolute minimum value and only one absolute maximum value, and they're both guaranteed to happen in a closed interval as long as you have a continuous graph. So they'll ask for the values for sure, and they usually ask for the locations too, which are the x values. See, the absolute maximum, type in integer or a fraction. See, they're not going to take that 8.5. So we have to put 77/9. The absolute maximum value is 77/9, and that occurred at the critical number negative 1/3. See how it doesn't have to be at an endpoint? It can be at a critical number too. And the absolute minimum value was 5. And if you do have a tie, then it says separate with a comma, answers as needed. So you could have, there's only one absolute minimum value, but there could be multiple x's that make it happen. But the only x that made it happen here was negative 1, which happens to be one of the endpoints. But that's what's nice, is if you have a continuous function on a closed interval, you're guaranteed to get the one and only maximum value and the one and only minimum value, and they can only occur at endpoints or critical numbers inside the interval. So it usually keeps your list pretty short, unless you just have lots and lots of critical numbers in between the interval. So I do have a polynomial, that means it's continuous, and the given domain is a closed interval -5 to 5. So definitely we're going to check -5 and 5, and there may or may not be an absolute max or min at either one of those, but we're guaranteed to get a max and a min. So if they don't occur there, then they're going to be occurring at only the critical numbers. And since this is a fourth power, then we're going to have an x to the third for the derivative. So there could be up to 3 critical, or there are 3 critical numbers, but there could be up to 3 inside that interval of -5 to 5. So f of x equals x to the fourth minus 32x squared and minus 2 from -5 to 5. So the derivative would be, I'm doing the derivative to find the critical numbers, 4x to the third minus 64x, and the derivative of -2 is 0. So this is never undefined, but it could be 0 3 times. There is a GCF of 4x, and that would leave x squared minus 16. And that's a difference of squares, so x plus 4 and x minus 4. There are 3 critical numbers, and they're all inside the interval too. 0, -4, and 4. So we're going to have to try -5, these are the x values, -5, I'll put them in order, -4, 0, 4, and 5. We always have the 2 endpoints in a closed interval, and then we ended up with 3 critical numbers that were all inside the interval, so we didn't get to eliminate any like we did last time. So we have 5 calculations to do into the original function, and we're guaranteed to get at least one highest and lowest in here. Now, suppose they were all the same thing, that would only happen if you had a horizontal line. So, but they're going to be different values. There can be some ties, but this is where having a calculator that can do this quicker helps a lot. I need to plug in -5 first, so parenthesis -5 parenthesis raised to the 4th power minus 32 parenthesis -5 squared minus 2. So f of -5 is -177. We don't even have to calculate f of 0, it's literally right there, -2. So now I'm going to do f of -4 by pressing second enter, and just back up on top of the 5s and type 4s. -250. 58, sorry, -258. That's the smallest one so far. And then I want to do +4, so I'm going to do second enter and delete the negatives off the 4s. Delete. Oops, too far. Delete. So f of 4 is, we got a tie, -258. And then I need to do 5 lastly. Type over the 4s with a 5. F of 5 is -177. when you have even exponents, that often happens where you get repeated answers on the negative side versus the positive side. But in these 5 answers, even though some of them repeated, out of these 5, the highest one is the -2. So that's an absolute maximum value of -2, and it only occurred at x equals 0. There's an absolute maximum value of -2. The graph will never get higher than -2, and it occurs at 0. And then there's only one absolute minimum value. It's -258. That's one answer, even though it repeated. But the x's are what are repeating, -4 and 4. It happened at both of those. So the minimum value is -258, which is unique. But then what's not unique are the 2 x values that made it happen. And in this problem, all the answers happened at critical numbers, but none of the endpoints were any of the answers. So 2 problems ago, we had only the endpoints were answers and the critical number wasn't. And now then we had one where one came from an endpoint, one came from a critical number, and now we got it where they both came from only critical numbers. So you never know ahead of time how that's going to shake out, but that's what's nice is you only have to check the endpoints and any critical numbers in between. Okay, now we got a rational function. Rational functions are continuous everywhere except any of their vertical asymptotes, the spots that make the denominator 0, which could be holes in the graph too. Okay, so we got 6 plus x over 7 minus x, and the domain is -7 to 0. It is a closed interval. Six plus x over 7 minus x. -7 to 0. Plus x, 7 minus x. Okay, so this is a quotient because I have a function of x in the numerator and the denominator. So I got to use the quotient rule. Second times the derivative of the first, which is just +1, since that's a linear piece, minus the first. The derivative of the second is -1 on that linear piece, all over the second squared. We can clean up the numerator. This part times 1 is itself, 7 minus x. Here you got this negative, and this negative could turn to a positive, and then this would just be 6 plus x. If there was only one negative, you'd have to distribute it in to the parenthesis. Here we get a little lucky that the x's cancel out. So the derivative is 13 over 7 minus x squared. So what would make this equal 0 or be undefined? A fraction is 0 when the top only is 0. And it's undefined when the bottom is 0. The top can never be 0 because it's always going to be a 13. And the bottom would only be 0 when x equaled 7. If you had 7 minus 7, 0 squared would be 0. But it turns out that's not a critical number if it also makes the original undefined, which it does. So 7 minus 7 makes the original undefined because there's actually a vertical asymptote there. So you can't have a critical number at a vertical asymptote since there's nothing there, literally. So that's the only caveat to the rule that the critical numbers are anything that makes the derivative 0 undefined unless they also make the original undefined. And that's what happened here. But the good news is that means there's no critical numbers anywhere, and there's no critical numbers between -7 and 0, obviously. So all we have to check are the endpoints. There are no critical numbers to have to check. And what that really means is one of these two is the maximum and one is the minimum, because in a closed interval, we're guaranteed to get each of them. So plug in -7, and you would get -1 in the top, and you would get +14 in the bottom. 7 minus a -7 is 14. So -1/14 is that value. And if I plug 0 in, the x's disappear, so you get 6/7. So negative is smaller than a positive. This is the absolute minimum. The absolute minimum value is -1/14. The absolute maximum value is 6/7. And they both occurred at the two endpoints. The minimum occurred at -7, and the maximum occurred at x equals 0. So the maximum occurred at x equals 0 with a value of 6/7. Your selection, your second answers. Your selection, your second answers are correct. Your first answer is incorrect. Okay, I didn't read how they wanted it. Oh, round to 2 decimal places. Okay. Usually they prefer fractions. I made the classic mistake of not even reading it, just assuming that's what they wanted. So they want 0.86 apparently, which is strange. 0.86. Usually they prefer exact answers. And then x equals -7 is where that other answer was. -1/14 is -0.07 to 2 decimals. So we're guaranteed to get one of each when there's a closed interval, and if all you have are the endpoints, then each endpoint is going to be one or the other. Okay, so here's one where the chain rule would apply. X squared minus 45 to the 1/3 power. Derivative would be 1/3 times the base. Decrease the exponent by 1. 1/3 minus 1 is -2/3. And then derivative of the inside would be 2x. So I could have a 2 and an x in the numerator. Right there. The denominator would definitely have this 3. And then we could drop this to the bottom, which would make it +2/3. There's the derivative. So this derivative could equal 0 because the top would equal 0 at x equals 0. 0 makes the top of the fraction 0. And it doesn't make the bottom 0. So that's the one and only spot where the derivative is 0. So the original function is never undefined, so that's not an issue. The cube root of this is never going to be undefined. So that is definitely a critical number then. I have one value that makes the derivative 0 because it makes the top of the fraction 0. Now, I don't know that that's going to be a number I use because I forgot to write down what the closed interval is. The closed interval is -6 to 5, and 0 is in that range, so now we've got at least 3 numbers we're going to have to check. We always have to check the 2 endpoints, and then any critical numbers in between them. So it could have turned out that this wasn't in the interval, but it is. Okay, then what makes the bottom equal 0 will come down to what makes this 0. There's 2 numbers that make that 0, because that's a difference of squares, x plus 5 and x minus 5. So both -5 and +5 make the denominator 0. and neither of them make the original undefined because nothing makes the original undefined. And they're both in, well, one of them's actually the endpoint, so that counts, but it's actually an endpoint, so it's going to decrease how many numbers we have to check by 1. So if this 5, if they would have extended this out past 5, then I would have had to check 5 numbers. The 2 endpoints and the 3 critical numbers, the 1 critical number is the same as the endpoint because they could arbitrarily start and stop this wherever they want. So we need to, I'm out of room here, let's make a list of my possible x's, which would be -6, -5, 0, and 5. Plug them back into the original function, which is, you could change that to a cube root if you want, cube root of x squared minus 25. A 1/3 power is a cube root. So these calculators have a built-in cube root if you press math and go down to number 4, cube root. Cube root, first I'm going to plug -6 in. -6 squared is 36. 36 minus 25 is 11. Cube root of 11, and let me check if they want fractions or decimals. Probably decimals, yeah. 2 decimal places. Type an exact answer for the x value, but they want 2 decimals for the value of the max or min. So the cube root of 11 is 2.22 to 2 decimals. If you plug in -5 or +5, this will be 25 minus 25 is 0. The cube root, any root of 0 is 0. So both -5 and 5 give you a value of 0. And if this one doesn't give me a negative value, then I'm going to have a tie for the absolute minimum. But 0 squared is 0. 0 minus 25 is -25. You can do a cube root of a negative. It's only a square root of a negative you can't do. So this will be the minimum, actually, because it's going to be the only negative answer. Cube root of -25 is -2.92. So the tie ended up not mattering because this is the absolute minimum and this is the absolute maximum. One of them occurred at an endpoint, another one occurred at a critical number. Not that that matters, but I'm just pointing out that you don't know ahead of time where these are going to happen. So the absolute maximum was 2.22 at x equals -6. The absolute minimum was -2.92 at x equals 0. Okay, so similar question. Similar, but it does have exponential in it. Let's try this one. What number are we on now? This is number 10. There is another half to this section. That what happens if you don't have a closed interval. So that's, I want to definitely make sure we do at least a couple of those. So x plus e to the -3x. And the domain is -3 to 3. So we do have a closed interval. The derivative of x is 1. The derivative of an exponential is itself at first, times ln of e, it's ln of the base, but ln of e is 1, and then times the derivative of the exponent, which would be -3. So I'll get 1 minus 3 e to the -3x. That's the derivative. It's never undefined. Exponentials are negative infinity to infinity domains. No issues in their domains. It's never undefined. And could it ever equal 0 is a question. So I could subtract 1. Divide by -3. I'm going to put an ln on each side, natural log, because I want to get that x out of the exponent. That's the property of logs, that you can bring that down in front. So -3x times ln of e, which equals 1. So that'll cancel. That's the reason for choosing ln, so you can make that e go away. ln of 1/3. And divide by -3. X is this mess, so it's just curiously, what is that? Close to natural log of 1 divided by 3 is -109, and then if you divide by -3, it's positive 0.366 approximately. And that is between -3 and 3. So we've got we always have the two endpoints no matter what. And if that's all you have, then you got your max and min between the two. But now there is one critical value, and it's in between them, so we got to include that somehow. And I don't know how they want that rounded, round to, type an exact, okay, that's going to be weird. Okay, so as an exact answer, it would be -1/3 ln of 1/3. That's the exact value of it. But to test what it's equal to, we can probably use this decimal if we don't round it. Okay, so I need to plug in, let me do this decimal while it's still on the screen. So I need to plug this long decimal into this x and into this x. So I'm just going to hit plus, and it'll say answer plus. So I've got the decimal here plus e. Second in the division button gets me e. Raised to the, I'm going to put a parenthesis because it's -3x. So -3 times that answer again. And then the two slots where I say have answer, it's going to grab that whole long messy decimal. So all we have to know is, I'll just put 0.366 here. Is this going to lead to either the highest or lowest answer or not? 0.6995 and so on. They're not going to take that answer, but, or they won't take this answer, but this you would round to 2 places apparently. Okay, but if the other two answers are both higher and lower than that, then this one won't even matter. So let me do 3 next, put a 3 right here and a 3 right there. So you would get 3 plus e, 3 plus e raised, and if I just do it in my head, 3 times 3 is 9. So to the -9, that way I don't have to put parentheses around it. 3 plus e to the -9 is 3.00012, but approximately 3.00. So already this one's higher than that one. So if this one turns out to be lower than this one, then we won't have to mess with the messy decimals. So now we need to do -3 plus e raised to the -3 times -3 would make the whole exponent 9. And that's a huge number. So that one's the maximum. And that means our messy decimal is the minimum. So the highest answer I got out of all these was the one at x equals -3. So they want exact answers for the location, although that's exactly, what did I say, -3. Nothing unexact about that. And then this is where they want that rounded to 2 decimals. Yeah, at round the absolute maximum to 2 decimals. So 8100.08. And then unfortunately the minimum, I guess they want me to type it this way. That's the only way to have it as an exact answer. Whoops. ln, and then let's go like this. There, that's the exact answer, literally. It's approximately 0.366, but they don't want an approximate answer. They do want an approximate answer here, and you would have to add 1 to that 69 and make it a 0.70. Okay. So that was one with an exponential at least. Okay, so next, this is good. So for the first time, we're on number 11 now, and it's not a closed interval. It's an infinite interval. X is greater than 0. So here's really the only thing you can hope for on this kind. First, I'm going to look for critical numbers as always. 6x plus 81 over x squared plus 5. And you could write 81 over x squared. I would write that as 81x to the negative 2. So you can use the power rule. I wouldn't do the quotient rule here because the 81 does not have an x attached to it. If it's just a constant, you don't have to do the quotient rule. It'll take a lot longer. And then our interval is anything greater than 0, which is an infinite interval. So intervals can be closed, open, or infinite. And the rule about the endpoints only applies to closed intervals. So if you have an open interval where it's like parentheses instead of brackets, or if you have an infinite interval that goes to infinity or negative infinity or both, then that previous rule doesn't work anymore. So let's first find the critical values, and then I'll tell you what happens here. The derivative of 6x is 6. I shouldn't have put a plus there. The derivative of this would be negative 2 times 81, negative 162, x to the negative 3. And then the derivative of 5 is nothing. So 6 minus 162 over x to the third. So this would be undefined when x equals 0. That would make the bottom 0. X equals 0 makes the bottom 0, and therefore the derivative would be undefined, but it would make the original undefined as well because the original had x squared in the bottom. So we lose that as a possible critical number. And then does it equal 0 ever is the next question. So we could add this fraction to the other side and get 6 equals 162 over x cubed. Then you could multiply both sides by x cubed. Divide both sides by 6. So I've got x cubed equals 162 divided by 6. Let's see if that divides evenly. Yep, 27. So the cube root of that is 3. 3 is the only number that makes the derivative 0. And the only number that made it undefined didn't matter because it makes the original undefined. So I have one and only one critical value. Critical number. So this is the second rule of this section 6.1. If you have any interval at all, whether it's open, closed, or infinite, so it could even work if we had a closed interval. If you have any interval at all, and it turns out there's only one critical value, one critical number, if this critical number can be shown to be a local max or min, then it's automatically an absolute max or min. So that would be my next goal, is to see if it's a local max or min like we did last chapter. And the second derivative might get long and messy, so I would do the first derivative test here and pick anything less than 3 like 0 and anything bigger than 3 like 4. Plug this into the first derivative and see if the signs change. Although I can't put 0 in because it makes it undefined. So let's use 1 then. So put a 1 right here. 1 cubed is 1. 162 divided by 1 is 162. And 6 minus 162 is negative 156, but more importantly, it's negative. So the original graph is going to be decreasing until I get to that critical number. And then it's flat for that one moment in time, because that's a spot where it makes the derivative 0. So if the other side is increasing, then we have a local minimum at 3 by the first derivative test. And then by this rule, this is called the critical number theorem. If you only have one critical number in any interval, and it turns out to be a local max or min, it's by the critical number theorem, it's also an absolute max or min automatically. So what would be f prime of 4? 4 to the third power is 64. 162 divided by 64 is about 2.5, but 6 minus 2.5 is about 3.5. And again, we don't care what it equals exactly. The point is that it is positive on that side of the critical number. So that means the original graph is increasing on that side. So by the first derivative test of the previous chapter, then I know this 3 is a local or relative minimum. This is a local minimum. And because 3 is the only critical number in the entire interval, then it's by rule an absolute minimum as well. So if you have an open interval or an infinite interval, this is your only shot at getting an absolute max or min. You won't be able to get both of them either. It's going to be one or the other only. And if you think about a graph that may be like a parabola is a good example, it goes down and goes back up again. So it has an absolute minimum. The vertex is the absolute minimum, but it does not have an absolute maximum. So it's not that you always have to get an absolute max and an absolute min. You only have to get one of each when you have a closed interval. If I stop the graph arbitrarily somewhere, then I'm going to have an absolute max and an absolute min. But if I let it go forever, in some cases it'll go up or down forever, or maybe both. We saw one earlier where it went both up and down and there was no absolute max or absolute min. So those are your two big rules in this section. If it's a closed interval, then check the endpoints and any critical numbers in between, and you're guaranteed to have a max and a min, absolute. If it's not a closed interval, then you have to hope there's only one critical value in whatever interval they give you. And then if there is, it's still not a guarantee you're going to get an answer, but then you got to check, is it a local max or min? If it is, then you get the absolute max or min along with it. So there is an absolute minimum at x equals 3 for sure. And then we could get the value by plugging 3 back into the original function. So 3 squared is 9. 81 divided by 9 is 9. 6 times 3 is 18. So 18 plus 9 plus 5, the minimum value is 32. And there is no solution to the absolute maximum. It may not be that there isn't one, but we just can't tell is the problem. So we don't say definitively that it doesn't exist, but we don't have any way to know. Okay, so what is left here? We're already 50 minutes in. Average cost, okay. Here's a cost one. That one looks like it'll take a while. Okay, see, this one doesn't seem so bad. This is similar to one we did already. Find the derivative of this, get all the critical numbers. It is a closed interval. So you would definitely be checking 4 and 19. And then if any of the two, there's going to be two critical numbers. If any of them are between 4 and 19, then you would include them in your list of things to check. Okay, so let me just do maybe one more of these. Okay, find minimum value of the average cost for the given function. Okay. So you got, in business, you have, this is called a cost function when they put C of X. C of X is your cost function. What's it cost to run your business or any part of the business? This is problem 14. So it's x cubed plus 37x plus 432. Average cost is when you take the cost function and divide by x. Think of like in an average where you add them up and divide by how many there are. So if you divide the cost function by x, you get what they call average cost, which they just put a bar over the c. So it'll take an x away from x to the third, make it x squared. It'll take an x away from that, make it just 37. But then on the 432, it would put that over x. Or you could think of this as 432 times x to the negative 1. So find the minimum value of the average cost. So the minimum value, we're guaranteed to get it because we have a closed interval here. There's going to be definitely a minimum, absolute minimum, and definitely an absolute maximum. And for first part, A just wants from 1 to 10. The minimum value of the average cost. So I need to do the derivative of the average cost to find any critical numbers in there. So the derivative of x squared is 2x. The derivative of this is nothing. And this would be negative 432 x to the negative 2. Which you could then put it back in the denominator as x squared. And the denominator being 0 would cause that to be undefined, but so would the original, so that we lose that one. There's not a critical number coming from an undefined spot. What would make this equal 0 is more interesting. You could add this fraction to the other side and get 2x equals the fraction 432 over x squared. Multiply both sides by x squared. X cubed, 2x cubed, but I'll go ahead and divide by 2. (216). The cube root of 216 is 6. Because 6 times 6 times 6 is 216. Cube root of 216 is 6. Now, what's also interesting here is that's the only critical number. So I only have one critical number in the interval 1 to 10. If I could show that that was a local minimum, then it would be by default an absolute minimum too. But that could take longer to check. And it may turn out that it's a local maximum or that it's nothing. And then I would have wasted my time doing that. But that rule works for any interval. It doesn't matter if it's open, closed, or infinite. If there's only one critical number in any interval and it's a local max or min, then it's also an absolute max or min. But it would probably be less work just to do the first rule since I do have a closed interval. and just use the endpoints and the critical number, and I'm just plugging them back into the original, which doesn't take very long. To do the first derivative test might take longer, and I might not get the result I'm looking for. But here I'm guaranteed to get a local or an absolute max and an absolute min. So the answer is going to be one of those three. So then we need to plug it into not the original function, but the original average cost function, this one, because we did a derivative of the average cost. So plug 1 into this. What is the numbers? 1, 6, and 10 is what we need to plug in. So I need to have a 1 squared for right there, 1 squared plus 37, and then 432 divided by 1, which is obviously 432, but I'm going to type it this way so I can type over it with the other numbers too. So when I plug 1 into the average cost function, I get 470. So really I should put, let me cross this out. This is actually the average cost that I'm plugging this into. Now plug 6 in. Put a 6 here and down there. Or I can just hit second enter and change the 1s to 6s. That's only 145. So it's possible that could be the minimum. But if this one's smaller than 145, then this one will be the minimum. So put a 10 where the 6s are. And I'll have to do, over the 6, I can type the 1 from the 10, but then I'm going to need to insert a 0 to slide everything over. And is it the next answer smaller or bigger? It's bigger. So that, you wouldn't have known it at the time, but it would have turned out that if I used the critical number theorem, that I would have been able to show that 6 was a local minimum, and therefore it would have turned out to be the absolute minimum by default. But this rule worked just as well and probably was easier. So this is definitely the absolute minimum value. There's an absolute minimum of 145 at x equals 6. The minimum value is 145. Okay, and then they didn't want where it happened, but you can do the same thing for, would it change anything here? The only critical number was 6. 6 is not in this interval. So all I have to do is check the endpoints, and we already did 10. So I guess part B would be just as easy to add. All you have to do for part B is add 20 to this list. And really, you're not using the whole list, you're just using these two. So what would 20 give me? I have a closed interval from 10 to 20. 6 is not in that interval. And 1 doesn't matter because it's not part of the interval. So 458.6. And we're looking for the minimum only, apparently. This one's only about the minimum. So now 10 would be the absolute minimum. X equals 10 would be the location of the absolute minimum, because all I have are the two endpoints, and that one's smaller. So 180.2 would be the absolute minimum if I change the interval from 1 to 10 to 10 to 20. So that wasn't bad to do the part B, actually. I thought we were going to have to start all over again, but no. So at least you got one of those business problems there. We're almost an hour in, but I want to at least cover a little bit of 6.4. Whoops, this isn't where I wanted to go. 6.4. What's going on here is you've got multiple variables at once. So all the rules are the same, but you got an extra step each time you get to a variable that's not the variable of interest. Go back. Whoops, I didn't mean to do that. Come here. Okay. So 6.4, number 1. I've got an equation with x's and y's in it. 5x squared plus 4xy plus 2y squared plus 13y minus 5 equals 0. And the directions say find dy over dx. So that's the derivative of y with respect to x. So that means x is the variable of interest. But I do have some y's in here too. Okay, so this is a polynomial format, and it's all added and subtracted. So when you're doing the derivative, you just do it like you're doing a polynomial where all the variables are x, and you just go term by term. Here it's just power rule over and over again. So 5 times 2 is 10. X to the first power. Now let me show you on the end of this. This equals 0. The derivative of negative 5 is 0. If this was 13x, the derivative of it would be 13. But it's 13y, it's not 13x. So anytime you get a variable that's not the variable of interest, then what happens is it's like you multiply this by the derivative of that, which can be either written as y prime or dy over dx. So in other words, I'm going to put dy over dx because that's what they asked me to find, but remember, those are equivalent. Anytime there's a y, you do the derivative normally and you just attach a dy dx to it. But if you only have an x, you don't do that. So the derivative of 2y squared is 4y using the power rule, but then dy over dx since it's the y variable. So that just gets attached every time there's a y variable. Now, the reason I skipped this one till the end is this, in essence, is a product rule. And I can either pull the 4 out and do it without the 4, or I can put the 4 with the x. It's not a big deal either way. So I'm going to consider 4x the first function and y the second function. So I might not even have enough room to fit it all in here, so let me write it above real quick. So I'm doing the product rule. The first times the derivative of the second. The derivative of y normally would just be 1, but then you got to multiply by dy over dx anytime you're doing a y variable, a derivative of a y variable. So that's first times derivative of the second plus second. Now you don't do it if you're just writing it like that. And then times the derivative of the first, that's just 4. And you don't do it if you're doing the x variable. So 4x times 1 is 4x. And that does have dy over dx attached to it. But then plus 4y, I can put that there. Okay, so we've got 1, 2, 3, plus here, 4, 5 total terms here. Any term that has dy over dx, there's 3 of them, they need to stay on one side of the equation, and all the stuff that doesn't have dy over dx goes to the other side. So that's why I circled those 2. So I've got 4x dy over dx. I'm going to leave that one there. And then I've got a plus 4y dy over dx, and a 13 dy over dx. All of those stay on this side of the equation. And then I'm going to move the 10x and the 4y over. That'll make them both negative. And then it's like you're going to do a GCF, but you don't really do a full GCF. You're just going to pull out dy over dx, even if there's more that you could pull out. But they all have that in common. There's not even a GCF otherwise, but if this had been 4x, 4y, and 12, you wouldn't want to pull a 4 out. You don't do the full GCF, just the dy over dx. So that would leave 4x plus 4y plus 13 equals negative 10x minus 4y. And then you just divide everything by everything except for the dy over dx. Four x plus 4y over 13. I mean plus 13. So this cancels out. I've got dy over dx equals this fraction. We don't care how messy the fraction gets unless there would be some way to simplify it, but there often is not. It's almost like a formula that you're solving for. So, and since the question said find dy over dx, that's the goal, is just to isolate that. And then this will be a little hard to remember it all. So I'm going to go like this. Negative, let me need a fraction first. Fraction negative 10x minus 4y, that's in the numerator. The denominator is 4x plus 4y plus 13. So really there's not any new rules here. All the derivative rules are the same. But anytime you do a derivative that's not of the denominator, then you have to attach on dy over dx or y prime to everything, to each of those. Okay. Did I not simplify it somehow? Oh wait, I wrote it wrong. Okay, so that's 4y. Just a slight typo. But if you could reduce the fraction, you should. So that's what was my first thought, is maybe I could have reduced it. But once I looked at it again, we saw that I had 4x twice. Okay, so number 2, 7x cubed equals 2y squared minus 9y. And again, it says find dy over dx using, this is called implicit differentiation. Differentiation is the noun for doing derivatives, and implicit is when you have a mixture of variables. So it matters which one they want you to find. They asked me to do dy over dx. That tells me x is the variable of interest. And if I don't get x, then I just get one of these on any of the other variables. So power rule here would be 21x squared. That one is x, so I don't do anything extra to it. Then 2 times 2, 4y to the first, but I got to attach a dy over dx to that. Minus the derivative of 9y is 9, and then attach a dy over dx to that. So in an equation, if you put the x's on one side and the y's on the other ahead of time, or if it's already that way, then it saves you from having to move stuff around like I did in the first problem. So on the right side, we want to factor out dy over dx only, even if there's other stuff they have in common. And that leaves just 4y minus 9. So divide by everything but the dy over dx. And this one doesn't look as messy as the other one, just had less terms, so this cancels. Dy over dx equals 21x squared over 4y minus 9. So the answer always has a mixture of x's and y's. And that's why it's implicit, because we've got a mixture of variables. 21x squared over 4y minus 9. Okay, so maybe I'll try that strategy here. Number 3, 4 square root of x plus 4 square root of y equals 8y. So I'm going to keep x on the left side of the equation, and I'm going to move that one over to this side. It's probably helpful to do that, to have x's on one side and numbers on the other. Okay, then I would change square roots to 1/2 powers. That'll make the power rule easier. So this one is 4 times 1/2, 2. X to the 1/2 minus 1 is negative 1/2. But that's x, so we don't have to attach anything extra to it. The derivative of 8y is 8, but it's a y variable, so we need a dy over dx attached to it. And this is why if you put x's on one side and y's on the other, you might not forget to do that, because I know it's going to happen on every term over here now. So the derivative of this would be negative 4 times 1/2 is negative 2. Y to the negative 1/2 the same way that one was negative 1/2, but then a dy over dx. We could put this x to the negative 1/2 in the denominator and make it x to the 1/2 or even square root of x, but I'm not going to do that because in a second we're going to be dividing by stuff, and then we'll have fractions inside of fractions, which they usually frown upon. So dy over dx, pull that out. Every term over here has it. So there's an 8 and there's a minus 2y to the negative 1/2. Negative exponents are usually not very bothersome in calculus, so they don't mind them as much as they do in algebra. So it's usually okay to leave negative exponents in answers. So if you change those negative exponents to positive, you'd have a fraction inside of a fraction in both the numerator and the denominator. Now, the only issue is this fraction can reduce, unlike the first two that we did, because the denominator has a GCF of 2, leaving 4 minus y to the negative 1/2. So then if you factor out a 2, then you can cancel this 2 with that 2. But you can't cancel this 2 with the 8 or the 2 because of the minus right there. So does it say? It doesn't say if they want it simplified or not. So let me see if they take it unsimplified, so then you'll know whether you have to do that or not. 2x to the negative 1/2. My guess is they're going to say simplify this. 8 minus 2y to the negative 1/2. No, see, they took it. So you could reduce, but if you don't have to, then why waste time doing it or take a chance you might do it wrong? So it's always, that's one good thing about homework, is you can try stuff like that and see what's allowed and what isn't allowed. So the whole point of this is get dy over dx by itself, and you don't really care how messy the other side gets. It might be interesting to see would they take fractions inside of fractions, which normally is considered improper. Could try that on another answer one time. Okay, so this one is interesting. Let's try this number 4 here. There's an x to the 5th and a y to the 3rd multiplied together. So that's going to be a product rule right there. There's a 2x to the 3/2. That one's only about x. Equals 3y to the 8/3. That one's only about y. And a plus 3. The strategy of getting x's on one side and y's on the other isn't really going to help here, because these two are together, so no matter what side you put it on, it's not going to work that way. So I'll just do it as is. So do your product rule here. First, times the derivative of the second, start off with the power rule, 3y squared, but because it's a y, then you need a dy over dx attached to it. This, even though this is fractional, it's kind of nice because 2 times 3 halves, the 2's cancel. So that would be 3x to the 3 halves minus 1 is 1 half. That one's x, so nothing attached to it. And they're doing this on purpose apparently because 3 times 8/3, the 3's would cancel. And that would be 8y. 8/3 minus 1, 1 is 3/3. So 8/3 minus 3/3 is 5/3. And the derivative of 3 is nothing, so. And I almost forgot, see, dy over dx right there. Because that was a y variable. Okay, so I'm going to, here's a quick thing I could do is I like to put the equal down. And I'm going to leave the 3x to the 1 half here. That'll be the only term without a dy dx attached to it. I'll leave this one here because it's got dy over dx on it. And then all I got to do is subtract this one over to the other side. Well, we can clean that up and put 3x to the 5th y squared all together. And then you can factor out the dy over dx. There would be this 8y to the 5/3. And then there would be the minus 3x to the 5th y squared. And again, it doesn't matter how messy this gets. Apparently it doesn't even matter if you can simplify the fraction because we just found that out in the last problem. So literally it's all about just getting dy over dx by itself. So divide this. So right there. This cancels that. I got dy over dx by itself. The answer is messy, but shouldn't be a problem. 3x to the 1 half is the only thing in the numerator. Oops. 8y to the 5/3 minus 3, that's where you can't see it, minus 3 x to the 5th, it keeps moving, y squared. Oops. And this isn't going to help. Okay. First check, did I mistype anything again? 3x to the 1 half, 8y to the 5/3 minus 3x to the 5th y squared. Nope. Okay, then is anything wrong with it? First, derivative of the second. Yeah, I didn't finish. The product rule is what happened. So I was only halfway through the product rule right here. First times derivative of the second, and I forgot to do, and the second times the derivative of the first, which would be 5x to the 4th. So there's an extra term that doesn't have a dy over dx, so I could easily attach that here. 5x to the 4th y to the 3rd. And that's an easy correction because it'll just, I can put it in the front of the top, it doesn't matter what order it's in. 5x to the 4th y to the 3rd. Luckily that one didn't have a dy over dx attached to it, so it was easy to keep it on this side of the equation. So remember, product rule, first times derivative of the second plus second times derivative of the first. I got distracted by the, where was this part from? Yeah, see, I did that too soon was what happened. Okay, so, and you can put it in the front or the back of the top. It doesn't, the order doesn't really matter. Amount. Well, let me go up there. Okay. So here I wrote it in the front, but I can put it in the back. It doesn't matter. 5x to the fourth, y to the third. There we go. A brain cramp mistake. Those are always frustrating because you know what you're doing, but then it's wrong. And if it's a test, you don't get any chance to go back and redo it. Okay, so here's an exponential. This looks like a really good one, actually. Number 5, it's got an exponential, and there's even a product rule in the exponent. E to the x to the fourth y equals 5x plus 6y plus 9. So the right side of this is easier. The derivative of 5x is 5. The derivative of 6y would normally be 6, but since it's a y variable, dy over dx gets attached to it. Derivative of 9 is nothing, so that side's very easy. The derivative of this is, well, at first it's not so bad. The derivative of an exponential is itself. And if the base is e, then you don't get an ln part because ln of e is 1. And then you need times the derivative of the exponent, and that's the product rule part. So first times the derivative of the second, which would normally be just 1, but it's a y, so really what it'll be is dy over dx, 1 dy over dx, plus the second times the derivative of the first, which is 4x cubed. Okay, so I'm going to distribute this to both parts of that plus. And then I would put the x to the fourth first, then the exponential, and then the dy over dx. Plus, this right here would all go together in alphabetical order, 4x to the third y, and then the exponential in the back. So that's what that left side became. The right side was much easier. And now the goal again is get all the dy over dx's on one side. So you could leave this one here and move this one over. X to the fourth, e to the x to the fourth y, dy over dx, minus this, 6 dy over dx, equals, keep the 5 right there, and now this guy has to move over to the other side and become negative. Minus 4x to the third, y, e to the x to the fourth y. And this part right here is going to turn out to be the numerator of your answer. I have to pull a dy over dx off both of these terms. And what that would leave is this minus that. X to the fourth, e to the x to the fourth y, minus 6. And then you're going to divide by all of this stuff right here. I'm running out of room, so let me just do it like this. Place this where I can see it both at the same time. Okay, fraction. The numerator is 5 minus 4x to the third. Then there's a y, and then there's an e to the x to the, a lot of exponents inside of exponents, x to the fourth y. That's the numerator. The denominator should be this right down here, x to the fourth. E to the x to the fourth y. Okay. Let's see, nothing else in the directions. 5x, 6y, 5. Well, let me move this out of the way. 5x, 6y, 5, 6, dy over dx, that should be good. E, derivative of the exponent. First derivative of the second, second derivative of the first. That is strange. Four x to the third. 4x to the third y. E to the 4x, okay. I didn't drop anything, did I? 4x to the third y, e to the 4xy, okay. And then this one went to the other side, minus 6. Did I forget the minus 6? Oh, I forgot the minus 6, okay. Minus 6. Simple mistake again. It was right there and I couldn't see it. Hiding down at the bottom. Minus 6, okay. Yep, that's all it was. Okay, so let's see what's left here. This is, okay, here's something different. Okay, so first, find the equation of the tangent line at the given point of the following curve. Equation of a tangent line, that's talking about derivative anytime you're talking about tangents. So I've got x squared plus y squared equals 34. That's a circle.